So I asked you to write the notes. No? Did you all make notes? Only 3, 4 are there. What about others? Any idea? Okay. But I asked to write till which topic? Video number 12. What was it? I think it is dipole. I asked to write till dipole. How much did you write? There was one or two which were missing. The order was missing. You have to arrange it in the name. It will be LEC 01 LEC. The pre-recorded videos. So it was like this. Was the audio clear? So I'm assuming you would have gone through these topics, right? So electrostatic potential and capacitance. So what does it speak about? Okay. So here, if you see the chapter number 2, it is called as electrostatic potential and capacitance, right? Now, so if you see the previous chapter, it was called as electric charges and fields. So what did we mainly discuss in the chapter? We saw how the charges were distributed and what were the fields that were generated due to the different distribution of charges, right? So that's what we saw. Then what are we going to see here is we are going to see another term, which is an extension of the previous topic, that is field, called as electrostatic potential, right? So here we'll be discussing about two things. One is called as potential energy, and the second is called as potential. Okay. So here, when you talk about electrostatic potential energy, what comes to your mind? So when you talk about this, guys, set it fast. So when you talk about this electrostatic potential energy, right, what does it speak about? Right. So what does this word energy speak about? So whenever you see the word energy, it refers to work done. Right? Whenever you speak about the word potential, it means something related to configuration of the system. It relates to the configuration of the system. Electrostatic obviously refers to the charges which are at rest. Right? Now you see. So how do we define this electrostatic potential energy? It is the amount of work that is done, right? In doing what? In moving a positive charge from one point to another against the electrostatic forces. This is the simplest definition. There you would have written it as the amount of work done against the electrostatic forces to move the charge from infinity to a point within the electrostatic field, right? So if I have to put it simple, right? If you are able to calculate the amount of work done in moving a positive charge from one point to another, generally that one point is initially taken to be infinity. From one point to another against the electrostatic forces, then there is some amount of energy, potential energy, right? So let's visualize how this actually looks like. So if I take the source charge to be positive, if I take the source charge to be positive, then let's take this boundary to be infinity. And let's say there is a test charge which is placed at infinity, which is outside the electrostatic field, right? Now, this charge does not create any influence on this, right? Now, as soon as this charge is moved into the electrostatic field, as soon as this is moved into the electrostatic field, if I take this to be Q naught, what happens? Because of a finite distance, let's say x that is existing between them, right? There will be a force that is acting on Q naught, right? So what is the value of that force equal to? So the force is going to be equal to K into Q naught divided by x square, right? Q naught divided by x square. Now, if I move this charge by a small distance, dw, if I move through a small distance, dw, sorry, if I move through a small distance, dx, then there is a small amount of work that is done, which is given as dw, which is given as f into dx. Right. Basically, if you see, when you talk about work done, right, work done can either be written as f vector dot s vector, or work done can be written as f vector dot integral of f dot dx. Right. So when will we use this and when will we use this? This is used when the force is constant, and this is used when the force is variable, when the force is a function of displacement, right? We use this. So dw is equal to f into dx. So what is going to be the value of f? It will be k into q naught divided by x square times dx, right? This is going to be the value of dw. Then if I need to calculate the total work done, what should I do? I need to integrate it in such a way that it is going to be k into q naught divided by x square times dx. Clear with this? So q naught will come out of the integral. So integral of dx divided by x square. So where did you move the particle from? Let's say you move the particle from infinity to some distance r. Initial distance will be taken to be infinity and the final distance will be taken to be r. So what is going to be the value of work done? So kq square's integral is, you will already have it in your notes. Integral of 1 by x square minus 1 by x. W is equal to K Q Q naught in integral of infinity to R and something. So it is equal to K Q into Q naught into minus 1 divided by X from infinity to R. So substitute the upper limit. So it will be K Q R plus K Q Q naught divided by infinity. So what will be that? Minus K Q Q naught divided by R. And this work done to move the particle from infinity to point P is going to get in the form of electrostatic potential. Right? This is what happens. Yeah. Okay. Yeah. Let me know once you're done. Done? So, listen. When you speak about absolute potential energy, right, the object is moved from infinity to a point. Whereas when you speak about potential energy difference, right, you calculate it as UA minus UP. Right. So this is potential energy difference. If you take one of the points to be infinity, then it will change accordingly. 1 minute. UAP is actually final minus initial. So UP minus UA. It is not like relative values. UAP means the potential energy when the object is moved from A to B. It is the final potential energy minus the initial potential energy. So here I want to stress on one point. When you look at the potential energy, right, it is giving you a negative value, right? So the negative value here indicates that the electrostatic force is conservative in nature. Right? So we need to say that the electrostatic force is conservative in nature. So the meaning of conservative forces, the amount of work done between any 2 points is path independent. Means if you have 2 points, if you are moving an object from A to B, you move it like this, you move it like this, right? Or you move it in this way. The amount of work done when you move the particle from A to B is path independent. It is going to be of the same value. That is what we call it as conservative in nature. Am I clear with this? Right? Shall I proceed? Right. So, if you look at the name of the chapter, it is actually not electrostatic potential energy. It is actually electrostatic potential. Okay. So, this is going to be the next topic of our discussion. So, if you see, there is a very slight difference between electrostatic potential energy and electrostatic potential. It is something like this. When you talk about potential energy or potential, you start with the word, the amount of work done only. Right. But if you say the amount of work done per unit charge, means if you are able to calculate the amount of work done per unit charge, then this physical quantity is given a name called as electrostatic potential, represented by the symbol V. Okay. See, I repeat it again. Electrostatic potential energy, if you define it like this, it means absolute, meaning the object is moved from infinity to a point. Similarly, when you talk about electrostatic potential energy difference, then the charge is moved within 2 points within the electrostatic field. Similarly, you have a concept called as electrostatic potential. So when you need to define electrostatic potential, it is absolute value. Where is the object moved from? The object is moved from infinity to a point. Guys, are you able to understand, or you want me to go in depth? I'm assuming that you have made notes. If you want me to go in depth, I'll go. Did you all make notes? No, right? I saw the app. I could see only 3 or 4 made it. Okay, there was a mistake also. That was not the actual videos which I intended to upload. It was a mistake from my side. I put it as lecture 1 to 12. No, they're actually broken into different lectures. Meaning this topic itself will be for 10 minutes. I took it in deep, but by mistake, some other videos have come in. I came to know after she told me. I didn't check that. You want me to explain? I'll do it. I wanted to save time, but again, today it'll be lost. It's fine. We'll see. Did you all understand what is electrostatic potential energy? Is there any doubt in that? Listen to this. When you talk about electrostatic potential, right, there's a very important term here. If you are able to calculate the amount of work done and you divide it with the charge that is actually moved, meaning if you take this to be the source charge, this to be the test charge, right? When you move this Q naught from infinity to some point P, what is the amount of work that is being done? In terms of magnitude, it is K Q into Q naught divided by, we just now wrote it, K Q into Q naught divided by R, where R is what? R is the distance from the point charge to the point where the charge is moved, right? So it is K Q into Q naught divided by R. So if this is going to be the amount of work done, then this is what is getting stored in the form of electrostatic potential energy. So the derivation till this step is same. If at all you are asked to derive electrostatic potential, till this step you need to follow whatever you did in the previous case. The only extra part is you will write V is equal to W divided by whatever charge was moved. So the amount of work done per unit test charge is what is called as electrostatic potential. So KQ into Q naught divided by R, the whole divided by Q naught. So answer will be KQ divided by R. Here you see I didn't consider the minus sign because I took only the magnitude. Okay. So if you see, how is this, what is going to be the unit of this electrostatic potential? So unit is going to be amount of work done is measured in joule per this coulomb. So joule per coulomb is going to give us volt, and it is going to be capital V. Right. So electrostatic potential is defined in terms of volt. Am I clear with this? So if you observe, right, U is given as minus K into Q naught divided by R. V is given as KQ divided by R. So in the previous chapter, if you observe, there is a quantity which is similar to this, which is KQ naught divided by R square. There is a quantity which was similar to this, not exactly the same. It is electric field. That is why what you can do is you can relate these two quantities. That's what we are going to do ultimately, right? As we progress, that is what we'll be doing. All right. I hope you're able to understand what I'm saying, right? So whenever you need to define force or whenever you need to define potential energy, the minimum charges required are 2. Whereas whenever you need to define potential or whenever you need to define electric field, the number of charge required is 1. Because look at the numerator, there is only 1 charge. Whereas look at the numerator here, there are 2 charges. Here, see, since the mistake this time was on my side also, I did. Next time, if there is something given, I want everybody to come. Or else I'll not let you insert. There is no point coming and sitting because it is an insult to people who are coming. I can see some of them have taken notes. It's a waste of time for them because they're listening to the same story again. There's not respect to them. Next time onwards, I'll not have. Is the point clear? I've already informed this. Okay. So next time, whenever I'm giving work, I want to see everybody submitting it. Or else don't come if you yourself don't come. You want to send you. Is the point clear? Let me proceed. Okay. Now, the question is electrostatic potential due to a point charge. So what is the value of electrostatic potential due to a point charge? That's what we calculated. No, V is equal to W divided by Q naught. It is going to be KQ divided by R. Are you able to understand? So it is going to be KQ divided by R. And this value is to be remembered. So this is going to be the electrostatic potential due to a point charge, and it is very, very important. Right. Now, see, for all these things, I'll give you the correct videos. You can all can again have a look at it. Okay. Okay, moving on to the next part. So electrostatic potential due to a system of charge. See, suppose you have multiple charges like this, Q1, Q2, Q3, something like this, which have, and due to the system, let's say you need to find the electrostatic potential at a point which are at a distance R1, R2, and R3. Okay. Then the total potential due to the system is given as potential due to the first charge plus potential due to the second charge plus potential due to the third charge. Right. The only difference is, listen to this carefully. When I talk about electric field and force, what kind of quantities are they? Scalar or vector? They're vectors. Whereas when you talk about potential, energy, and potential, what are they? Why is it? Why are they scalars? Because work done. So work done is a scalar quantity. So when you're dealing with scalar quantity, right, you need to take the sign of the charge into consideration. Okay, you need to take the sign of the charge into consideration. So what is going to be V1 value? It will be KQ1 divided by R1. That's what is going to be the V2 value. KQ divided by R2 plus K into minus Q3 divided by R3. Am I clear with this? Right. So this is how you calculate the electrostatic potential due to system of charges. So when they just use the word electrostatic potential, right? By default, you should understand that the first point was infinity. Okay. So you need not add this point. This line is not needed. Okay. Okay. So look at example 2.1 from your textbook. Example 2.1. Page 55. Right. So the question says, calculate the potential at a point P due to a charge of 4 into 10 power minus 7. Right. So there is a charge of 4 into 10 power minus 7 coulomb, which is located 9 centimeter away. So R is equal to 9 centimeters. So 9 into 10 power minus 2 meter. So first let's do this part. So this is part A. So it's very simple. What do you have? You have a point charge, right? What is the value of it? 4 into 10 power minus 7. Due to this point charge, at point P, we need to calculate the electrostatic potential. So what is going to be the electrostatic potential at point P? It is going to be KQ divided by R. So K is going to be 9 into 10 power 9 into Q is 4 into 10 power minus 7. The whole divided by R is 9 into 10 power minus 2. 9 and 9 are gone. So it is going to be 4 into, this is going to be 10 power minus 2. This will go to the numerator. Sorry, this is 10 power 2. This will go to the numerator as 10 power 2. So it is going to be 4 into 10 power 4 volt, or you can also write it as 40 into 10 power 3 volt, or you can also write it as 40 kilovolt. All the three mean the same. Am I clear with this? So in your textbook, they have stopped it with 4 into 10 power 4 volt. You can write in either of those. Are you done with this? Right. So if you see the next part of the question, they're saying, hence, obtain the work done in bringing a charge of 2 into 10 power minus 9 coulomb from infinity to the point P. Okay, that is the first part of second question. And the second part is, does the answer depend on the path along which the charge is brought? Okay, let's do the first part. So whenever there is a question of work done, right? Whenever there is a question of work done where one charge is moved from infinity to a point, right? There are two ways in which you can solve. One is either directly calculate the potential energy, right? You can either calculate the potential energy, take the magnitude alone. Okay, when you calculate the potential energy, it is going to be Q naught divided by R, where Q is this 4 into 10 power minus 7, Q naught is 2 into 10 power minus 9. You take that and substitute it here. That is one way. Or if you look at this part, right, this KQ by R is going to be electrostatic potential. So this Q naught multiplied with electrostatic potential is going to give you work. Since in the previous case, you already calculated the electrostatic potential, our job is easy here. What you need to do is, you need to take the charge that you move, multiply it with the previous value that you have. I hope it is simple, right? So both the ways are right. But the smarter way would be, whenever you know the potential and whenever you know the charge which is being moved, multiply both. It is like this value. You know that there is a charge Q naught, which is placed in the presence of an electric field E. Then when they ask you the force, you'll write F is equal to Q naught into E, right? In a similar way, work done will be equal to Q naught into V, right? So here, work done will be equal to Q naught into V. What is the value of Q naught? 2 into 10 power minus 9 into what is the value of V? 4 into 10 power 4. So how much is answer going to be? 8 into 10 power minus 5 joule. Right? Next part of the question is, does the answer depend on the path along which the charge is brought? Answer is no. Answer is no. And the reason being, electrostatic forces conservative in nature. Electrostatic forces conservative in nature. They've taken the electric field and all those things in there. See, what they're doing is, if you take this to be the path, on the path, they'll draw the electric field and again resolve it and do it. So work done will be path independent. Any arbitrary infinitesimal path can be resolved into two perpendicular displacements. So if you take this path, it can be resolved into two perpendicular displacements. One will be like this and the other will be like this. Okay. One along the r vector and one perpendicular to the r vector. The work corresponding to the later will be 0. So this one. Right? Because see, when you take this into consideration, this is how the electric field is going to be. Right? So in whichever path you are going to bring, right? In whichever path you are going to bring, if you take a small infinitesimal path, you resolve it into two components, one like this and one like this. When you calculate the work done due to the other parameter, it is going to be 0. That's what they're doing. So what they're doing is they're taking this Q naught into E, multiply it with the dx. I told you, work done is equal to F vector dot dx vector. No, the perpendicular component will get cancelled out in all the situations when you take multiple parts. But that's a complicated way of explaining. Rather, what you can say is, conservative. Because the definition itself clearly tells you that the work done is against the electrostatic forces. Okay, not here, the definition which I told you. Work is done against the electrostatic forces. Okay, and this 2.2, let's go to this 2.2. So 2.2 is page number 58. Page number 58. See, there are two charges, 3 into 10 power minus 8 coulomb and minus 2 into 10 power minus 8 coulomb, which are located 15 centimeter apart. So 3 into 10 power minus 8 coulomb and 2 into 10 power minus 8 coulomb with a negative sign. They are located 15 centimeter apart. Right. At what point on the line joining the two charges is the electrostatic potential 0? Take the potential at infinity to be 0. So if you look at the line joining these two charges, okay? So if I take this to be A, if I take this to be B, what I'll do is I can take a point here which I'll call it as P1. I'll take a point here which I'll call it as P2. And I'll take another point here which I'll call it as P3. Okay. So I don't know at which point the electrostatic potential is going to be 0. What I'll go is I'll go in the sequential order. So suppose I calculated at point P1. Okay. So if I take this distance to be x, so distance from charge A to P1, if I take it to be x, okay, I'll call it as x1. If I take it as x1, then what is going to be the potential at point P1 due to the charge at A? It is going to be K Q1 divided by x1 plus K minus Q2 divided by 15 plus x1. Right? So as per the question, the sum of potentials contributed by both the charges put together should be equal to 0. If I do that, then K and K will get cancelled. Then Q1 divided by x1 will be equal to Q2 divided by 15 plus x1. So what is the value of Q1? 3 into 10 power minus 8 divided by x1 is equal to 2 into 10 power minus 8 divided by 15 plus x1. I didn't take the minus sign here because I've already taken it here. So 10 power minus 8 and 10 power minus 8 are gone. So when you cross multiply, 3 into 15 is going to give us 45 plus 3x1 will be equal to 2x1. So which implies 45 will be equal to negative of x1. So what does this imply? x1 is minus 45 centimeter, which is not possible because this is not displacement, rather it is distance. So distance cannot be negative. So this clearly indicates that this is a point where the potential cannot be 0. Am I clear with this? So at this point, the potential cannot be 0 at all. Right? So this is about the point P1. Now, what about the point P2? This was 3 into 10 power minus 8. This was 2 into 10 power minus 8. So when I take it like this, if I take this to be P2, then let me take this distance to be x2. Then how much will this distance be? It will be 15 minus x2. right? So at P2, if I write Vp2, it is going to be equal to K Q1 divided by X2 plus K into minus Q2 divided by 15 minus X2. Am I right? So the sum of these two values put together should give me a 0. So K and K will get cancelled. Q1 divided by X1 will be equal to Q2 divided by 15 minus X2. So cross multiply again. So Q1 is how much? 3 into 10 power minus 8 divided by, oh sorry, here it is X2. By X2 is equal to 2 into 10 power minus 8 divided by 15 minus X2. 10 power minus 8 and 10 power minus 8 are gone. So what will happen? 45 minus 3x2 will be equal to 2x2, which implies 45 will be equal to 5x2, which implies x2 will be 9 centimeter. So, but the point to be noted here is you should not write it as 9 centimeter and leave it. What is that you're supposed to write? You need to write 9 centimeter from 3 into 10 power minus 8. Remember, in physics, whenever you're reporting the distances, right, you need to have the reference point. Because some will write 9 and some can write 6. Why 6? 15 minus 9. Right. That 6 centimeter would have been from 2 into 10 power minus 8, whereas 9 centimeter is from 3 into 10 power minus 8. So it is always very important to write this. Clear with this? Right. And what about P3? I'll give you 2 minutes time, calculate and tell. What about P3? Done. Good. What minus 45? Check it again. What 30? 30 from where? From where? You made a mistake in the minus. This minus is there. No, you would have taken minus here again. Did you do that? Did you take minus here? So did you write it as 2 into 10 power minus 8 only? So here it would have been 15 plus x3 and this would have been x3. You swapped it. Done. So I'll do it and see. Yeah. So if you calculate it at point P3, then this distance is going to be, let me call this distance as x3. Then the distance from the positive charge will be 15 plus x3. So this is going to be 3 into 10 power minus 8. This is going to be 2 into 10 power minus 8. So when you calculate the potential at point P3, it is going to be K Q1 divided by 15 plus x3 plus K into negative of Q2 divided by x3 if I equate it to 0. Then K and K will get cancelled. Q1 divided by 15 plus x3 will be equal to Q2 divided by x3. What is Q1? 3 into 10 power minus 8 divided by 15 plus x3 is equal to 2 into 10 power minus 8 divided by x3. 10 power minus 8 and 10 power minus 8 are gone. 3x3 will be equal to 30 plus 2x3. Take this 2x3 to the other side. x3 will be equal to 30 centimeter. When x3 is 30 centimeter, then you will say it is at a distance of 30 centimeter from 2 into 10 power minus 8 on the right of it. Clear? Right. So here, if you observe, right, one important point to be noted is, see, this kind of a question will come under two scenarios. One is they will ask you to find the point where the potential is 0. Second is they'll ask you to find the point where the electric field is 0. Okay. If at all there are two charges and along the line joining two charges, if you need a point where the electric field is 0, it is possible if you have a system of like charges also. So what I'm trying to say is, listen to this. If I have a positive charge here and a positive charge here, right? If I need to calculate a point, if I need to find a point along the line joining the charges where the electric field is 0, then if suppose this charge is 3 into 10 power minus 8, this is also 3 into 10 power minus 8. Okay, I'm just taking this kind of a situation. Now, if I take exactly the midpoint, then what will happen at that point is, electric field due to this positive charge will be to the right. Electric field due to this positive charge will be to the left, both being of the same magnitude. So they get nullified. So when you do the vector sum of both, they get cancelled out. Whereas, if in the same question I put, if I ask you saying that, tell me a point along the line joining the charges where the electrostatic potential is 0, you can never find it. Because electric field is a vector quantity, and here the values are getting cancelled out because of the directions, not because of the magnitudes. Of course, magnitudes also matter. They're of the same value, but the direction is helping the value to get nullified. Whereas, if you want to calculate the potential at that point, right, had the system been of like charges, then what would have happened to the potential at this point? They would have got added. They will never get subtracted. So for that value, for the potential to get nullified, the first and the foremost condition in the problem is you need to definitely have system of unlike charges, right? So here, the first condition is getting satisfied. You have unlike charges. Secondly, I took 3 points to calculate, right? P1, P2, P3. You need not take 3 points. You can take only 2 points going forward. And those 2 points will be closer to the charge with lesser magnitude. Listen to this carefully. The point where the potential will be 0 will be closer to the charge with lesser magnitude. In this case, which is having lesser magnitude. 2 into 10 power minus 8. Suppose the question was like this. 3 into 10 power minus 8 having the negative charge and 2 into 10 power minus 8 having the positive charge. Then where will the potential be 0? It will be closer to the charge with lesser magnitude, right? So where should it be? Still, it is going to be around this charge. One common mistake that we do is we see the negative sign and get confused. That is why I'm stressing on the point magnitude. I'm not stressing on the point of the nature of the charge at all. So in this case, is there a possibility for you to get the potential to be 0? along the line joining the charges. You will get it because the system is having unlike charges. Yes, that is possible. If at all it is possible, which will be the 2 points around which about which the potential will be 0? It will be somewhere around 2 into 10 power minus 8. So if you want, you can check and see. P1 we ignored because of the negative sign. P2 was at a distance of 9 centimeter from the charge of greater magnitude, but 6 centimeter from the charge of lesser magnitude. Then what about P3? P3 was also at a distance of 30 centimeter from the charge of lesser magnitude. But if you see for the charge of greater magnitude, it is at a distance of 45 centimeter. Am I clear? So you can use this logic directly and you can solve it. Suppose the same problem comes in competitive exam. Okay, you need not write all these steps. What you do is 10 power minus 8, 10 power minus 8 is there. No, just write 3 divided by 15 plus x3 is equal to 2 divided by x3 cross multiply, do it. You can avoid all these steps. There's only for CBSE purpose. In competitive exam, you can directly do it like this and you will get it. Right, these kind of questions are common. Am I clear with this? I think this was the last problem till which you copied, right? That was the last. Okay. Then we need to start with the electrostatic potential due to a dipole. Right, due to a dipole, like how we did in the previous chapter, we calculated the electric field due to a dipole at axial, equatorial, right? Here we'll be calculating the electrostatic potential due to a dipole at axial and equatorial. Then I'll go to another important concept called as equipotential surface. After that, I will show you what is the relation between electric field and potential. Right. Hopefully, I'll be able to do till that point tomorrow. Hopefully, let's see. Okay. So, any other questions from today's class? So, what I'll do is, I told you, I have the other set of videos which will be easy for you to understand. Whichever topic you have doubt, you can directly go and search that. I'll give you those videos. Okay. It will be with the name LEC01, LEC02. Just follow the order, you will understand. Okay. So that's it for today. So tomorrow's class will start with dipole. Both are right. Question per. You need to write both. X is equal to 9 in 45 is on the other side. Laptop you can't do it. Screen mirror panni. TV irka, smart TV, screen mirror. So if you go to page number 87, right? Go to page number 87. Look at the first question. What is the first question? Now, she asked a doubt, that is why I'm saying. So go to page number 87. Look at the first question. Read it carefully. Look at the second line. They asked at what point in bracket they have put yes, meaning there are more than 1 point. There is more than 1 point. So that is why you need to report 2 points, and both the points will be closer to the one with lesser magnitude. So here, can you tell me, without solving the problem, can you tell me where will the 2 points lie for 2.1, page number 87? One of the magnitudes is 5 into 10 power minus 8. Other magnitude is 3 into 10 power minus 8. Where will P2 and P3 be? Around 3 into 10 power minus 8. You should get it closer to that one. If you don't get it, your answer is okay. Okay. I'll see you tomorrow. You asked the doubt, no? See, 0.1 is you can use a logbook. Or what you need to do is, 1 minute, let me end this session.